So let's continue on with the multiplication rules and look at part 2. We talked in the last lesson about the conditional probability, and we said the probability of A and B is equal to the probability of A occurring times the probability of B given that A has already occurred. And we talked this is important if we're dealing with dependent events, where the likelihood of one thing is affected by whether another thing has happened or not. Well, if we take this formula and rewrite it, we're going to get this situation here. So now I can easily find the probability of B given A if I just know the probability of A and B both occurring, and I know the probability of A occurring. All I did was I took the conditional formula we had before, and we just rewrote it. So let's look at an example here. So we're talking about a box that contains white and black chips. If you read down, you notice that the probability of getting a black and a white chip on two chips is 15 out of 56. So we're pulling out two chips. Probability that one will be black and one will be white is 15 out of 56. Probability of getting a black chip on the first draw is 3 out of 8. Well, in this case, we're not replacing the chips. So the probability of pulling out a white chip on the second draw is affected by whether or not there was a black or white chip selected on the first draw. So now we're not looking for the and, we have the and. We're looking for the actual condition. What's the probability that I will pull out a white chip knowing that a black chip was pulled in the first pull? There's my setup. Well, I know the probability of pulling out a white and a black. That's 15 out of 56. The probability of pulling out a black chip on the first pull was 3 out of 8. I'm just going to do a division problem. Divide by a fraction, so we multiply by its reciprocal, or just use the calculator. So what we realize is there's a 5 out of 7 chance the probability that I will pull out a white chip given that a black has already been pulled is 5 out of 7. So 15 out of 56, it wasn't that likely I was going to get a black and a white. But if a black chip is pulled first, the likelihood I will get a white chip, it's 5 out of 7, so it's pretty high. Probability that Sam parks in a no parking zone and gets a ticket is 0.06. So he gets a parking ticket and he's parked in a no parking zone. The probability that he can't find a legal space and parks in a no parking zone is 0.2. On Tuesday he arrives, he has to park in a no parking spot. What's the probability that he will get a ticket? Sometimes it's easy to think of this as out of 100 cases because we're dealing with 0.06 and 0.20. So if you want to think of it without the formula for 1 second as just 100 cases, if he went 100 straight days, 0.2 probability of getting no parking zone, then 20 out of 100 days he would get a no parking zone. 6 days out of the 100 he gets a no parking zone and gets a ticket. Well, the 20 days that he parked in an illegal zone, we know 6 times he got a ticket. The other 14 times he doesn't. If you want to think of it that way without the formula, that might make things a little clearer for you. But if you want to go ahead and use the formula, the probability that he will park in a non-parking zone and get a ticket is 0.06. The probability that he will park in a non-parking zone is 0.20. So the probability he will give a ticket, given that we know he's in a non-parking zone, is 0.30, 3 times out of 10. If we looked at this with the 100 cases, that 0.2 on the bottom would represent 20 out of 100 cases. The 0.06 on the top is 6 out of 100. So if he went the entire year 20 times he would park in a no parking spot. Of those 20, 6 times he would get a ticket, which also is going to give you 0.3. It's just a different way to look at the same problem. The probability that a student will study for a test in math is 0.6. The probability that a student will study and pass the test is 0.54. We want to know what's the probability a student will pass given that he studied. I go ahead and I set everything up. In this case, it's 0.54 divided by 0.6. So there's a 0.90 probability, very, very likely, that if he studies, he will pass the test. If you want to think of this as 100 people again, there's 100 students, 60 of them study. Of the 100, 54 pass and study. So it's 54 of the 60, or 0.9. Either way is perfectly fine. Some people feel more comfortable with the formula. Some feel more with the real life situation. Let's talk about this at least idea. So if I'm picking 4 cards out of a deck and I am replacing them, what's the probability that I will get at least one ace? Well, this is independent. So we're getting away from the conditional for a second because I'm replacing the card. Well, the probability of getting at least one ace is the complement of getting no aces. Well, the probability of me getting no aces, the first pull wouldn't be an ace. 48 out of 52 are not aces. We replace it, so 48 out of 52, and so on and so forth. It's very unlikely that I'm going to get 4 aces, but at least one ace, pretty substantial here, 0.27, so 27 times out of 100. So if I did this experiment 100 times and picked out 4 cards, I'm going to get at least one ace 27 out of that 100 times. I just use the idea of the complement here to find the answer. It would be very difficult for me to find at least one ace doing 1 ace, 2 aces, 3 aces, 4 aces. It's possible, but using the complement was a lot easier. One more complement question. Neckwear Association reported that 3% of ties sold are bow ties. If 4 customers purchase a tie, find the probability. So in this particular case, we're trying to decide at least one person. Well, the complement would be nobody. Well, then if nobody buys any ties, that would be the 0.97. We know 3% are bow ties, which means 97% are not bow ties. So that would just be 0.97 times itself 4 times. And you get ourselves an answer. So if 4 ties are sold, we're talking about the idea that at least one of them is a bow tie, 0.115. So about 11.5 times out of 100. This is the second part of the multiplication.